What if reality doesn't exist until you look at it? What if the universe is not a solid, objective thing at all, but something far stranger, something that behaves more like information, probability, or even a computation? For more than a century, physicists have uncovered results that seem to bend common sense in half. And the deeper they look, the more the universe starts to feel less like a machine and more like a mystery. Today, we're counting down 10 of the most unsettling ideas in modern physics, from quantum measurement to holograms, hidden realities, and the possibility that the universe itself may be built on information. 10. The measurement problem. In 1927, at the famous Solvay conference in Brussels, the brightest minds in physics gathered to argue over one of the strangest discoveries ever made. Quantum mechanics had revealed something deeply unsettling. Particles like electrons and photons do not seem to have definite properties in the usual sense until they are measured. Before measurement, they exist in a kind of spread-out state of possibilities. That's where the famous double-slit experiment comes in. Fire particles toward two slits, and if you don't observe which slit they go through, they behave like waves and create an interference pattern. But once you place a detector to see the path, the pattern disappears, and the particles act like they picked one slit or the other. That raises a huge question. What exactly is a measurement? Niels Bohr's Copenhagen interpretation says quantum objects exist in superposition until observation forces a definite outcome. But that leaves us with a bigger mystery. Why should observation matter at all? That is the measurement problem. And to this day, it remains one of the deepest unresolved questions in physics. 9. The holographic principle. In the 1990s, physicists began asking a wild question. What if everything inside our three-dimensional universe is actually encoded on a two-dimensional surface? That idea is called the holographic principle, and it grew out of serious work on black holes. Jacob Bekenstein found that black hole entropy seems to scale with surface area, not volume. Then Stephen Hawking showed that black holes can slowly evaporate, which raised a terrifying problem. What happens to the information inside them? Later, Gerard T. Hooft and Leonard Susskind helped develop the idea that the information describing our universe might live on its boundary. Then in 1997, Juan Maldacena gave physicists a powerful mathematical framework, connecting gravity in one universe to a theory without gravity in fewer dimensions. In plain English, that means some versions of physics work equally well in a lower dimensional description. No one knows whether that means our universe literally is a hologram. But the math says the idea is not crazy. It's one of the most powerful concepts in modern theoretical physics. 8. The fine-tuning problem. Why does the universe seem so perfectly arranged for life? Small changes in the fundamental constants of nature would make stars impossible, chemistry unstable, and life as we know it unworkable. Even tiny shifts in the strong nuclear force could break the chain that produces the elements in our bodies. This is the fine-tuning problem. Physicist Martin Rees explored this in detail, and others have pointed out that the cosmological constant appears tuned to an almost absurd degree. Then there's the famous carbon resonance predicted by Fred Hoyle, which seemed to exist because carbon had to exist for life to be possible. So why does the universe seem so just right? There are a few possibilities. Maybe the constants were set by design. Maybe there are many universes with different constants, and we happen to live in one that works. Or maybe there's a deeper theory we haven't discovered yet. Whatever the answer is, the numbers look eerily precise. 7. Quantum entanglement. Quantum entanglement is the phenomenon Einstein called spooky action at a distance, and for good reason. When two particles become entangled, measuring one instantly tells you something about the other, even if they are far apart. That sounds impossible, but experiments have repeatedly confirmed it. The major turning point came with John Bell's theorem, which showed that if hidden variables were secretly controlling the outcomes, the results would follow one pattern. But experiments led by Alain Aspect in the 1980s matched quantum mechanics instead, not hidden variable theories. More recently, entanglement has been tested over huge distances, including satellite experiments spanning hundreds of miles. The unsettling part is this. Either information behaves in a way that challenges our normal idea of space, or space itself is not as fundamental as it feels. That is a radical idea. It means physical reality is not some separate substance hidden behind the equations. The equations are the reality. Whether you accept that or not, the fact remains. Math keeps predicting things before we observe them. Dirac's equations predicted the positron before it was discovered. Time and again, the universe seems to obey the logic of pure mathematics. 4. Many worlds interpretation in 1957. Hugh Everett. One of the strangest ideas in all of science. What if the wave function never collapses? In the standard view of quantum mechanics, measurement forces one outcome to happen. But Everett argued that all outcomes happen. When a quantum event occurs, reality branches. That means every decision, every quantum event, every microscopic chance may split the universe into parallel versions. For decades, the idea was considered too strange to take seriously. But it never went away. In fact, modern quantum computing has given many physicists a new reason to revisit it, because quantum systems seem to process information in ways that fit neatly with the many worlds picture. Whether it's true or not, many worlds offers a clean answer to the measurement problem. Nothing collapses. Reality just keeps branching. 3. The cosmic horizon problem. Look far enough into space, and you eventually reach the limit of what can ever be seen. That boundary is called the cosmic horizon. It's not the edge of the universe. It's the edge of observable reality. This becomes even stranger when you study the cosmic microwave background, the afterglow of the Big Bang. Some researchers have claimed to find unusual patterns and alignments in that ancient light, hinting at physics we don't fully understand. Then there's the Hubble tension. Different methods of measuring the universe's expansion rate give different answers, and the disagreement has become one of the biggest problems in cosmology. That matters because it suggests our best model of the universe may be incomplete. Not a little incomplete, deeply incomplete. 2. The death of objective reality. This is where things get really weird. Physicist Eugene Wigner once imagined a scenario in which one observer inside a lab sees a definite outcome, while another observer outside still describes the entire lab as being in superposition. Both accounts seem valid, yet they cannot both describe a single objective reality in the usual sense. Experiments inspired by this idea have now pushed the problem from philosophy into physics. The shocking implication is that what counts as a fact may depend on the observer. In other words, reality may not be a fixed, universal thing sitting out there independent of measurement. That doesn't mean anything goes. It means the universe may be far more relational than we ever imagined. 1. The architecture of a simulation. At the center of all these mysteries sits one idea that keeps returning in different forms: information. John Archibald Wheeler captured that with his famous phrase, "It from bit." The idea was simple, but profound. Physical reality may come from information, not the other way around. That's why so many bizarre features of physics feel connected. The speed of light is a hard limit. Planck length and Planck time appear to set minimum meaningful units. Quantum mechanics depends on measurement. Entanglement links distant particles. Holography suggests lower dimensional encoding. And some modern theories even find structures that resemble error-correcting codes. Put all of that together, and the universe starts to look less like a giant collection of stuff and more like a vast system processing information. That does not prove we live in a simulation. But it does explain why the idea is taken seriously by some scientists and philosophers. Maybe reality is not built from matter at all. Maybe matter is what reality looks like when information becomes organized in a certain way. Closing. So here's the big takeaway. The universe is not as obvious as it seems. The more we learn, the more reality looks strange, layered, and deeply tied to information, observation, and mathematics. And that may be the most unsettling truth of all, that what we call reality could be only the surface of something much deeper.
If you enjoyed this video, please like, subscribe to Palsa Lab and turn on notifications so you don't miss our latest uploads. At Palsa Lab, we explore space, science, astronomy, AI, and emerging tech, bringing clear explanations and fascinating discoveries. Have a question or idea? Drop it in the comments. Stay curious, keep exploring, and thanks for watching. See you next time.